So you can see that in synchronous machine, basically we are requiring two sets of excitation voltage. I mean to say, uh, you see, let us try to figure out what are the different windings in a synchronous machine. So on the rotor we are placing the field winding, which you can see on the screen. This is the field winding placed on the rotor, and the contacts of the field winding are accessible through this slip ring and brush arrangement. You can see this is the slip ring. This portion is the slip ring. Let me write it. This portion is the slip ring. This is the slip ring, and this portion is the brush. This is the brush portion. So with the help of slip ring and brush arrangement, we are able to have the contact, electrical contact with the field windings, which is placed on the rotor. So this thing is the rotor. This is your rotor, and this thing is your field winding. This thing is your field winding. This thing is a field winding. Now we require a DC source for energizing the field coils of a synchronous machine. So we can write that we require DC voltage source, DC voltage source for energizing the field winding, energizing the field winding placed in the rotor of synchronous machine, placed in the rotor of placed on the rotor, placed on the rotor, placed on the rotor, on the rotor. This is for this thing we are saying it for synchronous machine. Synchronous machine. Now the contacts with the field winding are made possible with the help of the slip ring and brush arrangement. So we can figure it out that even though the rotor is rotating, even though the rotor is rotating, even though the rotor is rotating, the rotor is rotating, the contacts with the contact with the terminals of field winding, with the terminals of field winding, the contact with the terminals of field winding placed on rotor, placed on rotor is possible due to slip ring and brush arrangement, is possible due to slip ring and brush arrangement, slip ring and brush arrangement as shown in the diagram. Slip ring and brush arrangement as shown in the diagram. Slip ring and brush arrangement as shown in the diagram. As shown in the diagram. So this is one winding, that is field winding. It requires a DC source. What about the other set of winding? The other set of winding is the armature winding. So armature winding is a balanced three-phase distributed winding. It is placed on the stator. So the armature winding should be connected to some alternating voltage source. So what happens? You are requiring then two voltage source. One is your DC voltage source, which is required for energizing the field winding. The field winding is placed on the rotor. Of course, rotor is rotating. but you are able to maintain contact with the ends of the field winding because you are having your slip ring and brush arrangement, which is shown here. We can see this is the slip ring and brush arrangement. So even though the rotor is rotating, you are able to maintain the contacts with the terminals of the field winding because of the slip ring and brush arrangement. So you are requiring a DC source for energizing the field winding of a synchronous machine. What about the armature winding? Armature winding is placed on the stator, and the armature winding, let me show here. Here I have shown the armature winding, or you can still refer to another diagram. Let me take you to another diagram. You can see these are the armature windings. This one I just mention it over here. This thing is your armature coils. Armature coils. This is also armature coils. This is also armature coils. This one is also armature coil. These are the armature coils. So armature winding is placed on the stator core and field winding is placed on the rotor. Now this armature winding needs to be connected to a alternating voltage source. The armature winding needs to be connected to the alternating voltage source. So I will, let me write this thing. Armature winding is connected armature winding is connected to an alternating voltage source, alternating voltage source. Now, depending on whether the synchronous machine is working as a generator or motor, two things can happen. If the machine is working as a generator, then the armature winding will export power to the AC voltage source, and if it is working as a motor, it will draw or it will import power from the AC source. So we can write that depending upon whether depending upon whether WHETH here, whether the synchronous machine is working as a generator or motor, is working as a generator or motor, what will happen, depending upon whether the synchronous machine is working as a motor or generator, it will be found that it will be found that in case of generating action, in case of generating action, armature winding will export armature winding will export power to alternating voltage source, to alternating or to AC voltage source, to which it is connected, to which it is connected, to which it is connected, to which it is connected. To which it is connected. So this is one thing we can understand, that it will export power to the AC voltage source to which it is connected. In case of motoring action, what will happen? In case of motoring action, in case of motoring action, what will happen? Armature winding, in case of motoring action, armature winding will import power from AC voltage source, from AC voltage source, AC voltage source to which it is connected, to which it is connected, to which it is connected, to which it is connected. So we have seen that we require two voltage sources. One is alternating voltage source which will be connected to the armature winding, and another is a DC voltage source which will energize the field coils. So that is the reason synchronous machine is also known as doubly fed machine, because we are doubly excited. Actually, the word doubly excited is more convenient. Synchronous machine is categorized in the category of doubly excited machine because we require an AC voltage source, and that AC voltage source will be connected to the armature winding, and we also require a DC voltage source for energizing the field coils. So that is the reason it is known as doubly excited machine. So if depending on whether the synchronous machine is working as a generator or motor, what will happen in case of generating action, armature winding will export power to the AC voltage source to which it is connected, and in case of motoring action, the armature winding will import power from AC voltage source to which it is connected. So in both the cases, motoring and generating, you need to connect the armature winding to an alternating voltage source, and depending upon whether it is working as a generator or motor, it will either export power or import power from the AC voltage source respectively. So now let me take to you that particular topic. We are actually trying to understand few concepts which are very important from the point of view of understanding the fundamentals of synchronous machine. So I have taken the cross-sectional view of a round rotor synchronous machine, and for making the things easier and simple, I have taken two pole machine. That means the number of poles for this synchronous machine is 2. So let us say we are having a field winding placed on the rotor and armature winding will be on the stator. So let me do one thing. Let me just first mention what is the nature of the armature winding which is placed on the stator core of a synchronous machine. It's a balanced three-phase distributed winding. So the nature of armature winding is balanced three-phase distributed winding. So what you can expect, that there will be lots of coil and those coils will occupy the stator core periphery. So the stator core periphery will be occupied by the armature coils. Now I would use the schematic representation. What is the meaning of the word schematic representation? Let me take a particular example for your understanding. Let us say that there are 36 number of coils. There are 36 number of coils in the stator core, the armature coils. Okay. So out of this 36 number of coils, 12 number of coils will belong to phase A, 12 number of coils will belong to phase B, 12 number of coils will belong to phase C. But when I am going to represent or give the schematic representation, I will not indicate the 12 number of coils for phase A. Rather, I will indicate only one coil for phase A. But yes, I have to make sure that the direction I have to make sure that the direction and magnitude of MMF which is developed by that single coil is same as that of the direction and magnitude of MMF developed by those 12 coils. I will again repeat, please be attentive. Please be attentive here. Let us say there are 36 number of coils in the stator core of a synchronous machine. So out of these 36 number of coils, 12 number of coils is belonging to phase A, another 12 number of coils is belonging to phase B, and the remaining 12 number of coils is belonging to phase C. So in this way you are making sure that you are allocating 12 coils for phase A, 12 coils for phase B, 12 coils for phase C. So you are making the winding balanced winding. The impedance will be same because the number of coils in each of the phase windings are same. But when I am going to draw the schematic representation of that synchronous machine, it is very time consuming and laborious to indicate those 12 coils on the stator core for phase A. So what I am going to do, I will indicate only one coil for phase A, but I will keep at the back of mind that it's not possible to have only one coil for phase A. There will be lots of coil. For example, in this case, I am saying there are 12 number of coils in phase A, but I will only indicate one coil for phase A. There has to be some justification for that. I am showing only one coil for phase A, but there are actually 12 number of coils. So what is the justification I am giving? I am saying that the magnitude and direction of MMF, magnetomotive force, developed by that one single coil is equivalent to the magnitude and direction of MMF developed by those 12 coils of phase A. So similar kind of approach I will take for phase B. In phase B also there are 12 number of coils, but I will indicate only one coil, such that the magnitude and direction of MMF is same, which is developed by one coil representing the phase B, and actually 12 coils which is there in phase B. The same thing goes for phase C. So let me indicate that one coil for phase A. So let's say that one coil for phase A is like this. This is coil side, let's say this is coil side A. So this is your coil side A. This is coil side A. This is coil side A dash. So this is coil side A. This is coil side A dash. Now what we do? Let us try to find out what will be the magnetic axis for coil A dash. So the magnetic axis of the coil A dash can be either directed from left to right or right to left, depending upon which coil side is carrying dot current and cross current. So let us do one thing. Let us place the direction of current carried by the field coils. Okay. So let's say this side is carrying cross current. Suppose this side is carrying cross current, and this side is carrying dot current. This side is carrying dot current. So these are your field coils. These are your field coils. So this thing is your field coils. This thing is your field coils placed on rotor. Placed on rotor. Now we need to calculate, or we need to find the direction of the magnetic lines of flux. So you can apply right hand grip rule. No trouble in that. So you apply right hand grip rule. So you will be able to find out what is the direction of the magnetic lines of flux. So dot means current is leaving the screen. Dot means current is coming out of the screen. So you imagine there is a conductor which is coming out of the screen, and the current carried by the conductor is coming out of the screen. Now hold the conductor with your right hand such that the thumb is out of the screen. Now you curl the four fingers, you will get to know the direction of the magnetic lines of flux. So this is the direction of the magnetic lines of flux. Now magnetic lines of flux are closed lines of flux, no doubt in that, obviously. So I have only shown this portion. If you want to show it like this, it will be like this, closed lines of flux. The same thing goes for here. Magnetic lines of flux are closed lines of flux, and yes, they do not intersect each other. This is also one important point which has to be thoroughly kept in mind, that they are not going to intersect each other. So now you know that inside the magnet, lines of flux are directed from south pole to north pole. Inside the magnet I am saying. So this will be your south pole and this will be your north pole. North pole, south pole. Now let me use some another color so that we are not getting confused. Let me use this black color only. So this is our south pole. and this is our north pole. So the same thing I can write it over here. This will be our south pole, this will be our north pole. Of course I have to mention the cross and dot like that only. This is cross current, this is cross current, this one is your dot current, this one is your dot current, dot current, dot current, this is also dot current. Now regarding the coil side A, so coil side A is like this one. This is coil side A, this is coil side A dash. So this is coil side A dash, this is coil side A. Now let us assume that this synchronous machine is working as a generator. Okay, so we are assuming the synchronous machine. Let us assume, let me write it here. Let us assume the two pole TWO2 two pole round rotor synchronous machine. Round rotor means cylindrical rotor or non-salient pole type. Two pole round rotor synchronous machine. Synchronous machine is working as a generator. Is working as a generator. So the moment we are saying that this is working as a generator, so there has to be a prime mover. So let us assume that the prime mover is driving the rotor in anti-clockwise direction. So let us assume the prime mover is driving the rotor, is driving the rotor in anti-clockwise direction, in anti-clockwise direction. So that is what we are assuming here. It is working as a synchronous generator. So if it is working as a synchronous generator, there will be a prime mover. Let's say the prime mover is driving the rotor in anti-clockwise direction. So I can indicate the direction of rotation for the rotor in anti-clockwise direction like this one. Now we have placed coil AA dash in this particular position. Now you have to pay little attention. Now where we should place coil BB dash? Coil AA dash is placed here. So coil BB dash will be placed in such a way that the peak of induced EMF in coil BB dash will happen after 120-degree rotation of the rotor. Okay. So based on this, you see right now south pole is in front of coil side A and north pole is in front of coil side A dash. So induced EMF in coil A dash is maximum. Now let us say this is also our positive maximum. We know that positive negative is just our convention. So let us assume that at this particular position which is shown on the screen, coil side A is in front of south pole, coil side A dash is in front of north pole. So let's say induced EMF in coil AA dash is maximum and let us say it is positive maximum. So let me write it at this position of the rotor, at this position of the rotor, at this position of the rotor, south pole is in front of coil side A, is in front of coil side A, and north pole is in front of coil side A dash, coil side A dash. So we say that EMF induced in coil A dash is maximum. Let's say this is your positive maximum. So after 120-degree rotation of the rotor, the peak will happen in coil BB dash, because as per definition, the phase angle, the time phase angle between coil A and B will be 120-degree, because coil A dash is belonging to phase A, coil BB dash is belonging to phase B. So between phase A and B there is a phase shift of 120-degree. So from that logic we are saying, so let's say if we want to just have an idea how much is your 120-degree, so this thing is your 90-degree, this thing is your 90-degree, this thing is your 90-degree. So what is your 120-degree? You add another 30-degree like this. So this thing is your 120-degree. So when the rotor rotates by 120-degree, in that scenario peak of induced EMF should happen in coil BB dash. So after 120-degree rotation, south pole will occupy here, this position, and north pole will be here. So let's say at that point coil side B is here and coil side B dash is here. So this is your coil side B dash, this is your coil side B. So you need to understand it thoroughly, that in what way we are placing the coil sides A dash, BB dash, CC dash on the stator core. The idea is very simple. I have to make sure that the peak of induced EMF in coil A dash and peak of induced EMF in coil BB dash, they has to be separated by a angle of 120-degree. That means the rotor should rotate by 120-degree. Then only this will happen. Now, by the same logic or same reasoning, we will say that here we should have the coil side C. This is coil side C, and this will be your coil side C dash. Coil side C dash. Because after another 120-degree rotation, it will happen, na? Let me draw over here so that it is there in front of you. So 120-degree means like this one. So this angle is also say 120-degree. This angle is also 120-degree. So coil CC dash is like this. So the same thing I will draw it over here. This is your coil side C. This is coil side C dash. This is coil side B. This is coil side B dash. Now we have been able to indicate the three coils for the armature winding. Now you can see that if you want to find the direction of induced EMF, or the rather not direction, the word induced EMF polarity is more appropriate. So what will be the magnetic axis? So let us do that. So let me continue with the same notation and direction. This south pole is at the top portion, north pole is at the here. So let me draw here. This will be your south pole, this will be north pole. These are your cross. These are your dot current. These are your dot current. This is again cross current. These are your dot current. And we are saying the prime mover is rotating the rotor in this direction. We are having coil side A here, coil side A, coil side A dash, coil side B, coil side B dash, coil side B, B dash, coil side A. Now let me bring it little bit down. So this is a coil side A dash, B dash, C dash. This will be C dash, C. Now, what is the induced EMF polarity for this one? So, we will again apply that modified Fleming's right hand rule. If you remember, yesterday I have told that let's say we are interested in finding the induced EMF polarity in coil side A. Okay, so we want to know what is the induced EMF polarity in coil side A. So what we will do, we will assume, actually see, the rotor is rotating, but just to apply Fleming's right hand rule, we have to apply this kind of modification, but that does not mean that rotor is stopped, it is not rotating. Rotor is still rotating, but we are assuming that rotor is not rotating, but the coil side A is moving in a direction opposite to that. So you see, actually the peripheral speed of the rotor is in this direction. If I draw with a line, tangent line, this is the peripheral speed of the rotor, this one. This is the peripheral speed of the rotor. So we will assume that this conductor is moving in an opposite direction to this. That means this one. And of course we will assume the rotor is stationary. So let me write it. This is the assumed direction of motion. Assumed direction of motion. Now I will write the word imagination in bracket. This is our imagination, okay? This is simply our imagination. This is not the actual thing. And this is the peripheral speed of the rotor. This is the peripheral speed of rotor. This is the peripheral speed of rotor surface. Peripheral speed of rotor surface. So we will assume the conductor is moving in a opposite direction to the peripheral speed of the rotor. Now what is the direction of B? That is the magnetic flux density B. So you can see lines of flux are from south to north pole inside the magnet. Inside the magnet I am saying. So this is the direction of B. Let me write BF, where F stands for field winding, because this magnetic field has been created due to the current carried by the field coils of the field winding. So that is the reason I am writing suffix F, BF. So now you apply Fleming's right hand rule. So your index finger will be pointing downwards, right hand index finger will be pointing downwards, and the right hand thumb will be along the direction of assumed direction of motion, which is the motion assumed for the coil side A. So you will find that it is having cross polarity. Now under south pole, you will definitely agree that coil side A, B dash, C are under the influence of south pole. So since coil side C dash, coil side A and coil side B dash, all these three coil sides C dash, A, B dash, they are under the influence of south pole, so they will have the same polarity in them. So these will be also cross. These will be also cross. Now if under south pole it is cross, obviously under north pole it has to be dot. So these will be your induced EMF polarity in coil side B, coil side A dash and coil side C. These three coil sides, coil side B, coil side A dash, coil side C, are under the influence of north pole. They are under the influence of north pole. Okay. So in this way, what we are going to do, we are going to put this dot and cross for the coil sides. Now we can now figure out the, what should I say, the magnetic axis for these coils. Now let me tell you one thing. What is that? is that when we are going to find the magnetic axis of the coil sides A dash, BB dash, CC dash, we need to ensure that the same condition is prevailing for all of them. What is the meaning of that? Same condition is prevailing. I let you know. Let me make it small sized. So now let's say I am showing this coil sides here. This is coil side A, coil side A dash. This is your coil side P, coil side B dash, B dash. This is your coil side A dash. Now we have coil side C dash. Coil side C dash. Now I will make a copy of this diagram 3 in number, okay, so that we are in a better position. So these will be made in 3 in number. So let me do one thing, let me rearrange this in this particular way so that they are along the same line. Now have patience and be with me. I assure you, you will get definite return if you are staying with me and having some patience. So now we can actually make separate lines. These three are separate diagrams, okay. This is a separate diagram. This is also a separate diagram, no doubt. Now I will draw the rotor for these three positions. So this is the rotor I am drawing for the first portion. Now over here I am saying south pole is here, north pole is here, and accordingly you can put up the dot and cross. Likewise, for this diagram I am saying that south pole is here, north pole is here. And likewise for this diagram also, let me modify it. So over here I will have this south pole and north pole. So accordingly that dot and cross, they will also move. So let me put up those also so that so I am basically indicating the rotor positions, the rotor position at different instants of time. Let's say the rotor is rotating by an angle of 120 degree. So I have indicated the rotor positions for 3 time instants, and between any 2 time instants there is a degree of rotation by how many degrees? That is 120 degree. Now you can put the cross and dot accordingly. This will be dot, these 3 will be dot, this is your cross, these are your cross. Likewise, this south and north, if you want to show it, this will be cross here, cross, these are your cross polarity, these are your dot polarity, dot polarity. This will be again cross, these are your dot. So You see, in this case, peak of EMF will happen in coil AA dash. Let me write peak of EMF. Let me write the word positive peak because there will be negative peak also. In case of negative peak, north pole will be in front of coil side A and south pole will be in front of coil side A dash. So I am saying positive peak of EMF happens in coil AA dash. Happens in coil AA dash. This is for this one. Over here, what can we write? Let me adjust this one. Okay, let me write in this way. Positive peak of EMF happens in coil BB dash. Happens in coil BB dash. Likewise, here we can write positive peak of EMF happens in coil CC dash. Happens in coil CC dash. So what this thing indicates that the peak of coil A dash, BB dash, CC dash, they are occurring at an interval of 120-degree rotation of the rotor. So we can observe one more thing is that, what is that? Theta electrical is given by P by 2 theta mechanical. Okay. Now here in this diagram, what we are seeing that P equals to 2. So theta electrical equals to theta mechanical. Also note that rotor is rotating at synchronous speed. Synchronous speed means ns, which is given by 120 f by p. Now for f equals to 50 hertz, we need to drive the rotor by a prime mover at 3000 rpm. So we can say basically that for this particular case, space angle and time phase angle are same because of these two reasons. That rotor is rotating at synchronous speed and theta electrical and theta mechanical are one and the same. So I can mention it over here. Keeping in view these points, below 2 points, 2 points. Number of poles equals to 2. Rotor is driven at synchronous speed. Rotor is driven at synchronous speed. Rotor is driven at synchronous speed. We can say space phase angle, space phase angle equals time phase angle, equals time phase angle, time phase angle. Now also we can actually place the dot and cross like way. South pole under it is cross, so these will be cross. I will put the polarity direction of rotation. That is very important. Direction of rotation is anti-clockwise. Direction of rotation is anti-clockwise. Direction of rotation is anti-clockwise, like this. So this is your dot. This one is dot. This is also dot. Now what about in this case? Under south pole, which poles, which coil sides are coming under south pole? Coil side A dash is coming under south pole, so this will be cross. Under north pole, these three are coming, so this will be dot. This is again cross. This is again dot. This is again cross. This is again dot. Now similarly, I can place here under south pole, if this thing is cross. Under north pole, this will be dot. You can apply Fleming's right hand rule in a modified way. The manner I have told you to cross check these things. Cross dot. This thing is again cross. So you have to locate which coil sides are under the influence of south pole, which coil sides are under the influence of north pole. So then you can easily find it out. So now what do you find? That the peak, the positive peak of EMF happens in coil A dash at this instant, and positive peak of coil BB dash happens at this instant, this second diagram. So you see there is a difference of 120 degree. The rotor rotates by 120 degree. So you can see here, I can just make the comment that in this thing from this point to this point, rotor rotates by 120 degree. Rotor rotates by 120 degree. Again in this case also you can say rotor rotates by 120 degree. So there is a phase shift of 120 degree between the induced EMF in phase A, B and C, because you can see the positive peak is happening after a time lag of 120 degree. Now what you can find it is that instead of dealing with the MMF of the three coils separately, we will only take MMF which will be termed as the resultant MMF. Let me write it over here again, cross dot. So again I will put up this cross and dot for the field windings. The same polarity is being maintained so that we can have a better correlation among different diagram. So what was the way coil sides were placed? This is coil side A dash. So this is coil side A dash. This is same thing over here, coil side A dash. Then we have coil side B, coil side B, coil side B dash, coil side B, coil side B dash, coil side C dash, C dash. Now, as usual, we can apply right hand rule and find this is south and north pole, and we are saying prime mover is driving the rotor in anti-clockwise direction. So these are the cross and dot which you can apply by applying modified Fleming's right hand rule, and the coil sides under the influence of south pole will have same polarity. Likewise, under the north pole, the coil sides will have same polarity. This will be cross, this will be dot. Actually, you can mark it here if you want by some different color. We say this portion is under south pole. This much portion is under south pole phase. This is your south pole phase. South pole phase. And likewise, you can find it here. This one will be your north pole phase. This one is your north pole phase. This is your north pole phase. Now, there are three coils, so we will have 3 mmf. Okay, so if you just draw this cross and dot over here, also cross, this is cross, this one is your dot. So what is the magnetic axis for this coil? Cross means current is entering into the screen, current is entering into the screen means cross, dot means coming out. So mmf is in this direction. So this thing is your mmf for coil AA dash. This is the mmf for coil AA dash. Likewise, for BB dash, this is cross, this is dot. So where will be the mmf? So this is the mmf for coil BB dash. In a similar way for coil CC dash, this is C dash. So cross dot, it will be like this. Let me draw it. So this is the orientation of the mmf for this particular instance. So let me mention it. This is mmf due to coil CC dash, mmf due to coil CC dash. This is mmf due to coil BB dash, mmf due to coil BB dash, BB dash, and obviously this one is the mmf due to coil AA dash, mmf due to coil AA dash. Now what is the field mmf? Let us see. Field MMF is this one. This thing is your field MMF. This thing is your field MMF. Field MMF. Due to field winding placed on rotor. Due to field winding. Due to field winding placed on rotor. Placed on rotor. Now, what is to be noted here is that we will not take up the MMF for the three coils individually. Rather, we will take the resultant MMF due to the three coils. So this will actually simplify our analysis, and also it will be easier. Although the other approach is also equally acceptable, no problem in that. But still, for simplicity, we will do what? That we will only consider the result. We will not consider. Let me write first what we are going to not consider. We will not consider. We will not consider MMF of coil, MMF of coil AA dash, coil BB dash, coil BB dash, coil CC dash separately, coil CC dash separately. Separate. This is important one. We will not consider MMF of coil AA dash, BB dash, CC dash separately. We will take the resultant. We will consider the resultant MMF. We will consider. We will consider resultant MMF. Resultant MMF due to these three coils. Due to these three coils. Three coils. So that means what? We will always consider the resultant MMF. Now, resultant MMF will be aligned with the magnetic axis of that coil which is carrying the peak current. Okay, so let me mention this. Now, it is to be noted that resultant MMF, it is to be noted that resultant MMF will be aligned along the magnetic axis of that coil, along the magnetic axis of that coil which carries the peak current, which is carrying peak value of current. So this is something you need to remember it thoroughly, otherwise you will get confused. That first of all, we will not consider MMF of coil AA dash, BB dash, CC dash separately. We will consider resultant MMF due to these three coils. Now it is to be noted that resultant MMF will be aligned along the magnetic axis of that coil which is carrying peak value of current. Now, the resultant MMF, you can see here, this will have two components. It has got two components, vertical component and horizontal component. So this is the vertical component, say, and this is the horizontal component. Likewise, this one is also having this vertical component and this horizontal component. So these will cancel, na? These two vertical components will cancel. If you want to see that, these two vertical components will cancel. These two vertical components, vertical component of MMF cancels. So resultant MMF is aligned with the magnetic axis of coil A dash. It is shown here. We can write that resultant MMF is aligned with the magnetic axis of coil A dash. Resultant MMF is aligned with the resultant MMF is aligned with magnetic axis of coil AA dash. Magnetic axis of coil AA dash, and EMF AA dash will carry the peak current because EMF induced is maximum in coil AA dash, isn't it? So resultant MMF is aligned with the magnetic axis of coil AA dash. This is what we have seen here. So this is the reason that we will only deal with one MMF, and this resultant MMF will be termed as armature MMF, FA. This is also another point. Let me mention it. This resultant MMF will be termed as armature MMF. This resultant MMF will be termed as armature MMF, will be termed as FA, that is armature MMF. That is armature MMF. Armature MMF. A stands for armature. A stands for armature. Please note that here suffix A is not standing for phase A. Here A stands for armature. Suffix A stands for armature. So what do you now further conclude? That the orientation of armature MMF in space is not going to be fixed. It will also rotate because resultant MMF is aligned with the magnetic axis of that coil which is carrying the peak current. Now current is not going to remain peak always in coil A dash. It will be now going to C, B like that. So it is not like that peak is happening only in coil A dash. Peak of EMF is happening in both coil A dash, BB dash as well as CC dash. So that is the reason the orientation of the resultant MMF FA will not be fixed. It will rotate. It will move in space. So we can see that both armature MMF FA, we can call this to be your FA, and we can call this to be your FF. So FF, that is field winding, is rotating. Field MMF is rotating at synchronous speed because it is placed on the rotor. This thing is placed on the rotor. So field MMF FF rotates at synchronous speed. 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 Likewise, FA also rotates at synchronous speed. FA also rotates at synchronous speed. Now, there is one more point which we should think over. What is that? Let me tell you. It is not necessary that the time instant at which induced EMF is maximum, so at that instant also the current will be also maximum. That can vary, isn't it? Let me show you. Let me copy this. Let me complete the diagram once more. So we will now focus on this particular aspect, that the time instant at which induced EMF is maximum, will the current will be also maximum at that time instant, or it will differ? So now the answer to this question lies on the fact whether the current carried by the armature winding is leading, lagging, or it is in same phase with the voltage. Or in other words, you can say whether the armature winding is connected to a resistive load, to a inductive load, or to a capacitive load. Depending on that situation, I mean to say the armature winding has to be connected with some load, electrical load, because we are dealing with now generating mode of operation. So load will be electrical load only. So electrical load can be of three types. So depending on whether the type of the load is inductive load or capacitive load or resistive load, that thing is going to vary and differ. So let's say the armature is connected with a purely lagging load, 90-degree lagging load. So in that case, the time instant at which voltage or the induced EMF in the coil A dash is maximum, current may not be maximum. This thing is a very simple thing to understand. Let me draw a diagram that will be easier for us. So I will be now I will be depicting here rotor position for two time instant. Okay, I will depict the rotor position for two time instant. Why it is so? Because we are assuming the armature winding is connected to a load which is 90-degree lagging. 90-degree lagging means current peak will be 90 degree later than the voltage peak. So obviously, since the armature winding is connected with a 90 degree lagging load, so the current peak and the voltage peak are not happening at the same time. They are separated by a time instant of 90 degree. So in that 90 degree time span, you cannot expect the rotor to remain stationary or stand still. It will also rotate by 90 degree. So it will happen that, say, south pole has come over here and north pole has come over here, and accordingly this dot and cross portion, they will also move by 90 degree, no doubt. They will also move by 90 degree, no doubt. So let me complete the drawing. Now just be with me, have patience. I will, it is very important to place the diagram in front of you so that you have very easy understanding. So what we are trying to depict here, we will place here, we will depict here two position of the rotor, and the two positions of the rotor are separated by 90 degree time 90 degree rotation. Let us say use the word 90 degree rotation instead of the word time interval. So the rotor has rotated by 90 degree. So the rotor position will be depicted here. Here two positions of the rotor will be depicted. Two different positions which are separated by 90 degree rotation. So our diagram is complete almost. So here is the thing. So what we are assuming, the armature winding is connected with a 90 degree lagging load. Okay. So the rotor is still driven in anti-clockwise direction only, so it will remain like this. And regarding this cross and dot, you can check it. It will, this thing will be cross, cross. These are dots. This is dot. This one is dot. This one is dot. Dot. So cross dot. Now let me write it quickly. Now here I will put up this cross and dot, but now I have to be careful regarding something. I will write it over here instead of mentioning. These are your cross, this thing is your dot, this thing is again dot, this thing is your cross. The same thing is happening here also. This will be cross, this is dot, this one is cross, this one is dot, coil side A dash is dot, coil side B dash is now you need to be quite attentive over here. This is very important. This is indicating polarity of current. This is indicating current. Okay, so this is indicating indicating This is indicating polarity of current. Polarity of current. Not to be confused with induced EMF. Not to be confused. Confused with EMF polarity. And this is induced EMF polarity. This thing is your induced EMF polarity. Induced EMF polarity. Polarity in different coils. In different coils. So let me also comment on the rotor thing. So this is the rotor position. This is the rotor position. Rotor position at the time of maximum induced EMF, maximum or peak induced EMF, peak induced EMF in coil AA dash, in coil AA dash. But this is the rotor position. This is the rotor position let me rewrite it correctly. This thing is a rotor position. Rotor position when current in coil AA dash, when current in coil AA dash is maximum or peak. So what do you see that, let me mention it over here. The peak of current in armature winding happens after 90 degree. The peak of current, the peak of current in armature winding, the peak of current in armature winding happens after 90 degree. By that time rotor, by that time rotor also rotates by 90 degree. So this is something we need to realize it, that it may not be always happening that the time instant or the time moment at which voltage is maximum, at the same time current is also maximum. It depends on the load, the type of load with which the armature winding is connected. So we are assuming here armature synchronous machine is working as a generator, and armature winding is connected to a purely lagging load, that means 90-degree lagging load. So let me write that also, that synchronous machine is working as a generator. Here we are saying that synchronous machine is working as a generator synchronous machine is working as a generator, and armature winding armature winding is connected armature winding is connected to a 90-degree lagging load, to a 90-degree lagging power factor load. 90-degree power factor load is also known as purely inductive load. Purely inductive load. So we see here that the current peak is happening after 90 degree. So by that time rotor also rotates by 90 degree. So we can easily observe from the diagram that the effect of armature flux on field flux is demagnetizing. So what I will do, I will keep this entire diagram handy in front of us, and we will again let me copy this portion. So what we are trying to find here, that what is the effect of armature flux on field flux in case it is connected to a 90-degree lagging load. Okay, so we can plot the lines of flux, no problem in that separately. You can plot the lines of flux separately. Let us plot it. Let us copy this portion. This is one. Over here we have to erase this portion because we are interested in only plotting the lines of flux. So let us not have this one. So we are going to plot the armature flux and the field flux. Okay, we will plot armature flux and field flux. So let me copy this rotor portion separately. So this is the rotor portion. Okay. We are not able to see the magnetic lines of flux, but we can actually plot the pattern which is going to be taken up by the magnetic lines of flux. So that is what we will be doing. We will plot the pattern of the magnetic lines of flux based on some rule. That rule can be right hand grip rule, or it can be your right handed corkscrew rule. There are lots of rules which you have studied in your physics when you are in school. So you apply any of these with which you are more familiar and convenient. But the thing is that you have to plot the magnetic lines of flux due to current carried by the field winding, due to current carried by the armature winding, so that you have a ready-made and first-hand idea regarding the effect of the armature flux on field flux. So this is your coil side A, this is A dash. Now let us plot the magnetic lines of flux. So let me use this pink color. So the magnetic lines of flux we are going to plot like this for the current carried by the armature winding. This is the magnetic lines of flux. I will put up the direction shortly. So cross dot. So you can apply that right hand grip rule. You will see that this is the direction of the magnetic lines of flux due to armature current. So if you move along the line, these are your closed lines of flux. So this thing is your pi A. So this is armature flux. This thing is your armature flux. This thing is your armature flux. And what about the field flux? We have to plot the field flux also. We will plot it. Field flux. So cross dot. So for field flux, this is the direction of the field flux. This is the direction of the field flux. This is the direction of the field flux. So this thing is your phi f. This thing is your phi f. So this is your field flux. Field flux. Now armature flux due to current carried by armature winding. So armature flux due to current carried by armature winding. Flux due to armature current IA, and this is the flux due to IF. This is the flux due to IF. Field current, IF stands for field current. So we see that the effect of armature flux on field flux for 90-degree lagging load in case of synchronous generator is entirely demagnetizing, because they are in opposite direction. You can notice phi f and phi a are in opposite direction. So note that phi a phi a and phi f are in opposite direction. Are in opposite direction. Are in opposite direction. So what we have seen, that the effect of armature flux, the effect of armature flux, the effect of armature flux phi a is entirely demagnetizing, demagnetizing for a synchronous generator or for an alternator for an alternator connected to 90-degree lagging load, 90-degree lagging power factor load. Or you can say if armature current is lagging by 90-degree, or when armature current IA, when armature current IA, armature current IA lags by 90-degree. So in this similar way, you can find out the armature reaction in case if it is 90-degree leading load. You can figure it out that for 90-degree lagging load, if it is entirely demagnetizing, for 90-degree lagging load, if it is entirely demagnetizing, then for 90-degree leading load, it will be magnetizing. But this is for your generating action, remember, this is for your generating action, okay. So let it be up to this. If you have any question, you can ask me.